So I found this particular problem online. I'll take this opportunity to show you how to solve for it using a couple different strategies. It's up to you to decide what strategy works best for you and how well you know your geometry. So the first strategy I have here is keeping my x and y coordinate the same. A traditional up and right would be positive. So everything I do will be based on that reference point. Okay, so here we have a pipe of length 5 meters. The mass of it is 15 kilograms. And then we have a diagonal force here directed in the second quadrant with a magnitude of 160 newtons at an angle of 42 degrees above the pipe. All right, so here we go. The first thing you should identify is all your forces and where the pivot point is and where the force is being applied. The force of gravity for the pipe should be placed at the center of mass of the pipe, which is there in red in the diagram. And the magnitude for that would be 147 newtons if you take 15 kilogram times 9.8 meters per second. And then the next thing we should identify is the lever arm. For this particular diagram, the pivot is on the floor at the bottom edge of the pipe there. And that particular distance is going to be L over 2 because it is referencing center of mass. L here being 5. Okay, so the statement in the original problem says the length of the pipe is 5 meters. So 5 over 2 would be 2.5. But you notice right away that the lever arm and the force here due to gravity is not perpendicular. So you need to find the component of the lever arm that is perpendicular to the f of g, which I have dashed here on the bottom in the red. So this is in the x-axis, f of g lies on the y-axis, and that would make you perpendicular, which is what you need for torque. So if you find the magnitude of that length, it'll come out to be 2.07. Again, we plug in 2.5 divided by 2, and we use cosine here because this leg here is the adjacent referencing this 34 degrees angle, so therefore it's cosine. The next thing you notice up here is that the applied force F of t here is not perfectly left or up or down, so it's a diagonal, so therefore it implies that there must be components. So in the green here, this is your FTY in the vertical component, and then in kind of purple, this is your horizontal component, which I'll label F of tx. But to figure out what these things are, we have to do a little geometry. So here, the angle here will be 34 because it is the same as this angle down here. This diagonal, or aka pipe, is cut by 2 parallel lines. So the angle here must be the same as the angle there. That's 34, which leaves us with the little basic math here to find the angle where the purple line, aka horizontal axis, touches the applied force. We would just take 42 degrees given in the diagram, subtracted by 34 degrees, and that little angle there would be 8 degrees. Again, everything is referencing this particular coordinate system on the right, so it's important that you pay attention to the geometry here. And then from there, once we know the angle, we know the hypotenuse, we can just go ahead and find the magnitude of the components. So FTY here would be 160 sine at 8 degrees. Again, it's sine because this is really the vertical component, if you want, and that is the opposite of the 80 degrees, so we use sine. And the magnitude is going to come out to be about 22.27 newtons. And then we can do the same for the horizontal component. F of tx, I went ahead and calculated for you. So it'd be 160 times cosine of 8 degrees because this dashed line here is adjacent to the 80 degrees. So we need to use cosine of 80 degrees. Okay. But other than that, now we have to find our lever arm that's perpendicular. So the distance from the pivot to where this F of t is being applied is right there. And that distance is going to be 4 meters because the length of the pipe is 5. And then from here down to where the force is being applied, it's a distance of 1 meter. So the difference would be just be 4 meters. So it's important that you pay attention to the length and then, find what you need. But in this case, we can't use 4 meters because 4 meters and this F of t is not perpendicular. And then the lever arm 4 meters here in black, and F of tx is not perpendicular either. So we do have to do a little bit of, work. So let's go ahead and find the lever arm of the 4 meter here. So from here to here, if you can watch my cursor, that's going to form a right triangle. So the green dashed line down here, that'll just be 4 meters times cosine of 34, which would give us a leg of 3.31 meters. And this dashed green line on the bottom, of length 3.31 meter is perpendicular to f of ty. So those two components will go together, and that'll generate a counterclockwise torque. So that's done. But then we still haven't accounted for f of tx here. Again, f of tx is right there, but we can't use the 4 meters because it's not perpendicular. So we just have to find the vertical component of the leg, which is right here. And then this right here would just be 4 sine of 34, and that'll give us a length of 2.24 meters. And I went ahead and did a little animation there to move the component of the leg up there in the green. So you can kind of see that this is right angle. Again, when you do torque, everything has to be perpendicular. You can leave it down here if you want. It doesn't really matter. I just moved it up so visually you can kind of see where the 90 degrees form. Okay, and then from here you just have to identify what causes counterclockwise or clockwise torque. So from my perspective, this f of ty is going to cause the pipe to rotate counterclockwise. In addition, if you pull the pipe towards the left using this horizontal component ftx, it's also going to cause the pipe to rotate counterclockwise. However, if you cut the string, the weight of the beam will naturally cause the beam to rotate clockwise, aka falling down. So we have two force components that'll cause the system to rotate counterclockwise, and then we have the vector f of g causing it to rotate clockwise. So I'll just go ahead and do the math here for you. So I just did net torque is equal to torque in the counterclockwise direction, which is taken to be positive, and then subtracted from the torque in the clockwise direction, which traditionally is taken as the negative direction. Again, I've already accounted for the negative sign here, so pay attention to sign as usual. So I went ahead and found the magnitude of these things, and then from there, based on your answer, you can kind of tell the direction of the rotation. So I have f of tx, which is up here, times the level arm for that's perpendicular, which is 2.24 meters, color-coded there for you again. And then f of ty, which is up here. And f of ty uses this level arm, that's dashed line. Again, that's the relation drawn down here. I just moved it up there. It doesn't change anything. And then the length of that is 3.31 minus, because f of g is going to produce a counter torque, aka in the clockwise direction. So the weight of that times the level arm, again, which is down here. So you just have to do like a few triangles and make sure you use perpendicular components. And if you do calculator work, you should get a magnitude of 124.33. And I went ahead and picked choice C because that is the closest answer. And the direction is going to be counterclockwise because all this summation here, the 354.91 plus the 73.71, is a bigger positive number than the 304. Again, counterclockwise in physics is taken to be the positive direction, while clockwise is taken to be the negative direction, and the negative sign is there. So the fact that your magnitude comes out to be positive also suggests that in this particular problem, it's going to rotate counterclockwise. And here's the second strategy. Okay. So the second strategy is that you can tilt your axis like an inclined plane problem. Horizontal to the plane would be x, and then perpendicular to the plane, in this case, the pipe would be y. So to me, this looks like an incline problem with an angle of 34 degrees there. So if you keep the pipe as the x-axis, there's still f of g acting on it. Okay. But in this case, if you are going to keep this pipe as your x-axis, you notice your f of g is no longer in the y direction, so they're no longer perpendicular. But if you apply your prior knowledge from an inclined plane, you can find f of gx and f of gy super duper fast. And then from here, if you notice the animation that came up, nothing has changed since the last strategy. The pivot is here, the force is there, the level arm in this case would be L over 2. But you notice the force is not perpendicular to the level arm. So you can go ahead and find f of gy and f of gx, which just came up on the screen. Again, if you've mastered your inclined planes, these components, f of gy and f of gx, should be pretty quick to find. So the angle here is 34 degrees, which is the same as the angle of the slope, as I've done previous units. F of gy would just be f of g cosine of the theta. In this case, f of g is 147, cosine of 34 degrees, and then that should yield about 121.9 newtons. And then here's f of gx. F of gx, again, by definition, is f of g sine the angle of the incline, which in this case 34, and that magnitude would be 82.2. But what you notice here is that, again, when you do torque, you need perpendicular stuff. So here's L over 2, which is a distance of 2.5, because that's half the distance of the pipe. And you need the perpendicular stuff. In this case, perpendicular would suggest as f of gy. So why you can find f of gx, it's kind of useless in the strategy. So I'm going to go ahead and take it out of the slide here, just to clean it up a little bit. Okay. And in addition, you can also take out f of g, because f of g is not perpendicular to this level arm, which is along the x-axis based on this tilted axis system. So this is the x-axis, this is the y-axis, which is perpendicular. And then we can go ahead and do the same strategy for f of t. Therefore, f of t here would have a component in the y direction, and it will also have a component in the x direction. Okay, so if we do a basic math, stuff that comes up here, so the lever arm from pivot to where the force is, again, is 4 meters, and that is in the x direction already. Here's f of ty, which is what we need because x and y are perpendicular. Again, I kind of show you how to find f of tx here, but you don't need f of tx. F of tx is useless because it parallels the pipe, which is now in the x-axis, and you don't need parallel, you need perpendicular. So I'm going to, again, clean this up a little bit, take that component out of the way because it doesn't do anything for the torque. And using geometry, by the way, in case you didn't keep up, if this is 42 degrees and this is the x-axis, the green components in the y-axis, that would be 90 degrees, and this is 42 degrees, so the difference would be 48 degrees. So you got to make sure you do your geometry correctly, otherwise using the wrong angle is going to cause your outcome to be kind of whack. Okay. And in this case, if you look at it, the f of t will cause the pipe to rotate counterclockwise, while f of gy will cause the pipe to rotate clockwise. So really we just have a systems here of a difference of, that'll rotate. Again, if you start off with your physics function, net torque equals to F times R in this case, and just plug it in. FTY is right there, which is in the y-axis. And then how far is it from the pivot? It is a distance of 4 meters, which is in the x-axis, which is already perpendicular. And then F of GY here, which I found for you already in the screen, is 121.9. And how far is it from the pivot? 2.5. And these things are perpendicular already. And so you can just do calculator work, and it should yield also the same answer, or approximately the same answer due to rounding and stuff like that. Okay, so pick a strategy that you like. I kind of like the second one a little better, only because it is quicker, but that's assuming you've mastered your incline plane so that you're not tripping out on parallel and perpendicular components. The first strategy, I think, it's easier for kids to visualize because you're not tilting your axis. Everything is X and Y, and it's easier to keep things at perpendicular. All right, good luck. Don't be whack. Stay nerdy.